Hey everyone, Natasha here with a video on type 1 error control methods when you are planning to use contrast comparisons. So let's get started. All right, so in this week's lab, we are going to review planned contrast and type 1 error after implementing NANOVA. We will be really focusing on a hypothetical example here inspired by Shilin et al. In 2024 and Sopra in 2021, which actually compares the effectiveness of different pedagogical approaches to teaching art and programming. And so there are technically four different types of approaches here. There's the flipped class approach, the approach of deployment result improvement, the pair programming, and the active student centered learning. And these are all going to be compared on students' level of reported confidence when applying our code. And then what we know a little bit about these type of approaches is that the ASCL is actually the gold standard within this field, meaning that this teaching approach has actually shown differences. Whereas, for instance, the ADRI has actually led to poorer outcomes than some other techniques. However, we actually haven't seen all of these techniques compared to one another. And this is going to play a crucial role later on when we are making our contrast and actually trying to adjust for and control for that type 1 error. So definitely keep this in mind. All right. So I keep throwing around this word type 1 error. What is it? In plain language, type 1 error in relation to significant testing or hypothesis testing is the rejection of the null hypothesis when it is actually true. And the null hypothesis is often thought of as the nothing hypothesis. In this case, we're saying that nothing is different, right, in comparison from one point to another, or that there are no differences between one group or another group, or two or more conditions. Okay. In the context of our example, a type 1 error would be rejecting the null and concluding that there are differences in students' reported levels of confidence across these different teaching approaches, when in fact, we would technically want to retain the null and conclude that there are no differences. So, one more time, it is suggesting that there's a difference when there really is not. Okay, and type 1 error is by far considered the worst type compared to the other type of error that ends up happening. And this suggests that there are no differences. Okay. We can honestly can make decisions and implement procedures during our analytic process to adjust for this type 1 error. And we can do this through statistical techniques, right? To make sure that our techniques are not vulnerable to this problem. All right, so let's go ahead and review how type 1 error is related to mean comparisons, the whole purpose of this video here. When we compare multiple means using statistical techniques such as ANOVA and COVA-MANOVA, we actually end up increasing the probability or the possibility, the likelihood of a type 1 error. Whether the comparisons are post hoc, meaning that they technically were unplanned, or whether they are planned, I still want you to know this increases the possibility of a type 1 error. In the context of our study here, we have to think about all the hypothetical comparisons that we can make. For instance, we can compare the flip approach to the ADRI approach. We can compare the ADRI to the pair approach, and so on and so forth. We can even compare all possibilities here, right? All the simple pairwise comparisons. And what's even more extensive is if we went into complex comparisons, where, for instance, we took two approaches and we compared it to one. But one more time, highlighting here in this graph, The more number of means we go ahead and compare, the more likely or the higher probability of a type 1 error occurring. And we can really center this by the next topic of family-wise error rate. All right. A little bit about family-wise error rate. This is a term. This is a statistical term. And so it is also known as the family-wise error rate that helps us calculate the probability of making at least one type 1 error among a family, a group of multiple statistical tests, where M here in this little equation is equal to the number of statistical tests and can be calculated in the following way, where we go ahead and we take the difference between our alpha level, which is typically 0.05 in all psychological and education research, and we subtract it by 1, and we take that to a power of the number of statistical tests that we are doing, or another way that we can say this, or the number of comparisons that we are making, and then subtracting that powered value by 1. And so, for instance, in this particular example here, we could have made up to 6 different comparisons for simple comparisons. And so then a test at an alpha level 0.05, that normal p-value that we're always trying to compare to, would then create approximately 26.9% chance of at least a one type error approaching or suggesting that there's some sort of at least a one false positive in comparison to that 5%, which we really want. Okay. Now, I briefly mentioned up above that we could have either post hoc, these are kind of like unplanned comparisons. This is after you do an ANOVA and you weren't expecting there to be any differences among their groups. And so you had no plan for comparing them, right? And then there are also planned comparisons when those planned comparisons can actually be broken up into orthogonal versus non-orthogonal. And so we're going to be discussing these 3 different approaches to comparing our means. So there are multiple analytic techniques that can help us control for type 1 error when making multiple comparisons. All right, so one more time, there are multiple techniques that can help us control for type 1 error when we're making multiple comparisons, and they all depend really on whether we have a post hoc unplanned comparison approach, or we have a planned comparison, whether it's orthogonal or non-orthogonal. And so we need to really address the following questions to go ahead and to determine which analytic technique will help us control for that type 1 error. And one of the first questions we need to ask is, are these planned comparisons or ad hoc comparisons? In other words, for instance, a ad hoc comparison, as I already have noted, it would suggest that we had not one clue that we were going to find a significant F test, right? And so our post hoc test always actually really requires a type 1 error correction that is built into the method, because you are going to probably make lots of comparisons to find out where exactly those differences are after the omnibus test. Go ahead and suggest that there are differences. All right. So that's one of your first questions. Another question is that if they are technically planned, right? If they are technically planned comparisons, are those comparisons orthogonal? Meaning, are those comparisons independent to one another? Meaning that there is no testing of overlapping data. Or could they possibly be non-orthogonal, suggesting that the weighted comparison of group means is actually shared across other contrasts? In other words, there's dependence upon the contrasts or the comparisons that are being made. All right. And if technically they are non-orthogonal, you find out that there is some sort of dependence between these mean comparisons. It suggests that our type 1 error rate may increase because we are hypothetically testing rather the same hypothesis multiple times. And because the result mean comparisons are not independent. So that means you need to use a method to deal with type 1 error. Now, if your comparisons are technically considered independent to one another, there's no overlapping of data, you have orthogonal contrast, no additional correction is needed. You can go ahead and actually do and proceed with comparing each one of those means as if you were using a t-test. All right, so let's go ahead and talk about a little bit more about those type 1 error control methods. All right, and this is one more time if you have to go ahead and rely on a post hoc analysis or those contrasts, or AKA those comparisons, are non-orthogonal. And I'm simply going to highlight for here types of type 1 error control methods. I know that there are more out there, but just for the sake of this video, this is what I'm going to highlight. Okay, so control for family-wise error. All right, you have two types of approaches that are really highly thought of and often used here. We have the Dunn-Bonferroni, and we have the Šidák correction, aka the Dunn-Šidák method. And so I do want you to know that Bonferroni is usually synonymous with family-wise error rate. I mean, every single time I usually see someone controlling for type 1 error, they are applying Bonferroni's approach here. And so what I want you to know is that the Dunn test is like the standard Bonferroni correction, and it makes the significance threshold a little more stringent. And it does this by dividing the original alpha, usually at the 0.05 for psychology and educational research, by the number of comparisons being made. So we would take technically our 0.05 and we would divide it by 6 if we decided to do all the comparisons. And the Šidák correction, or the Dunn and Šidák method, I want you all to know that this is a statistical procedure used to adjust for the significance level for our alpha level of 0.05 when performing multiple hypothesis tests simultaneously. And this and tries to really make sure that we remain at the error rate that we want to be, even though we're making multiple comparisons. So it calculates an exact, slightly more powerful and less conservative threshold than the Bonferroni correction by taking that the number of comparisons being made to 1 over the comparisons. Okay. And then there's a second set of kind of approaches that we can go ahead and use to control for type 1 error. This actually falls under the umbrella term of false discovery rate. And really, what this is, it's a statistical method used in multiple hypothesis testing to control the proportion of false discoveries here, all the rejected nulls hypothesis and that they're technically supposed to actually be false positives, right? These are our type 1 errors. And so the way that we can go ahead and calculate our FDRs here is that if we take the expectation of those false positives over all of the possible discoveries, okay? So all of the possible outcomes here. And so, unlike the family-wise error rate that controls the probability of any false positive, which is very restrictive, FDR controls for the proportion of the false positives, and then making it so much more powerful than comparing all of or any of the false positives. And so I do want you to know this approach still can lead to a small number or small proportion of false discoveries. Okay. And so there are two different methods that I'm going to highlight here. Both have Hochberg in mind here. I hope I'm saying that right. So the Hochberg rank order contrast by their p-values from the smallest p-value to the largest. If the largest p-value is less than that family-wise error rate, you would reject the null for the previous contrast. Okay, one more time. You are going to order all of those p-values from smallest to largest, and you would start at the largest one and you would figure out if it is less than the family error rate, then you would go ahead and reject everything or all p-values that come or all contrasts that come before that p-value. And if that is not the case, then what you want to do is go to the second largest one and you want to take that family error rate and you want to divide it by 2. And then you want to take those two values and you want to compare them to each other, right? And if it's the case that that new largest value is less than that family error rate, then you would go ahead and suggest that that value and everything that comes after it, or rather before it, is actually when you would go ahead and you will reject the null. So let's try that again. So let's just say the second to the largest is not actually uh, less than that family error rate. Then you would go to the 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 third largest error rate there, okay? Or the third largest p-value rather. And you would compare it to the family error rate divided by 3. And if that third largest p-value is less than that family error rate divided by 3, then that particular contrast and all the contrasts that come before that one, you would then go ahead and reject the null hypothesis. All right. Okay. So you can definitely see how there is still a possibility of all of there being a small portion of false discoveries, right? And so then the next type of type 1 error method, right? That type 1 error control method is the Benjamin Hochberg approach. And this is one more time a false discovery rate approach. And it compares each individual p-value to a rank adjusted significance threshold, the total number of contrasts or ranks of those contrasts to determine which result is most statistically significant. And it's very, very, very similar to the Hochberg rank order. Very similar. Okay. All right. And so we can finally get into our example here. I do want you to know that in the context of our study, we have decided on comparing the means of all pedagogical approaches to the gold standard, which is the ASCL. And we're also going to be comparing the ADRI to flip and pair approaches to the confidence that students report when applying their R code. Right, so there are a couple things that we need to do before we actually get into this example here. And one of the first things that I can think of is that we need to go ahead and put our CSV file with all of our data into our working directory. So please navigate to that folder that you went ahead and you downloaded from my GitHub, which is now on your desktop. And here I have the teaching underscore R CSV file. Please move that CSV file to your working directory, which you have named either type 1 air lab or something of that sort. Great. Now I'm going to be able to access this. Now, another thing that I really want to do is I want to go ahead and I highly recommend this is that we split our screens between our HTML file and our RMD file. Okay. And so all I'm going to do is doing a drag and drop here. I'm going to navigate to that split screen here. All right, now I'm going to be able to follow along a little bit easier. And so now we can go ahead and we can start working on this example. We are first going to upload some packages. I'm going to initiate an R code chunk by using some keyboard shortcuts, and that was Option Command I to initiate that R code chunk. Okay. And then I'm going to type out a quick little a comment here or note with using that hashtag or that pound, depending on whatever you know that symbol as. And I'm going to type out packages. And then I'm going to type out library because I want to call in this package that has already been uploaded or downloaded in onto my computer here. So library, enter, and then dplyr. All right. All right. Perfect. So I have that package. Then once I go ahead and have that package uploaded, I can go ahead and start calling in my data or reading in my data. I'm going to one more time initiate an R code chunk, Option Command I. And so I'm just going to write out a note here. This is me reading in my data. And one more time, I do this just to show you that you should be leaving yourself comments throughout your whole entire RMD file, your script, or whatever you may use. So that way, for reproducibility purposes, if someone wanted to jump into this RMD file, they know exactly what you are doing. Okay, super important. Okay, and then I'm going to go ahead and I'm just going to call it in by using the read.csv function. So I'm going to first type out the functions that I need to use here, read.csv, and you can see it automatically populates. And in quotes, I need to go ahead and note that I need to read in that teaching underscore r.csv file. And then I'm going to assign this reading in of this file to an object, and this object is going to actually be stored in my working environment over here. So I need to name it something. In this case, I'm going to name it teach underscore R for teaching R. You can go ahead and run this line of code either by coming to the end of it or the middle of it and hitting Command Return, or you can go ahead and even use that play button if you would like to. So Command Return. All right, I run that and I know for a fact that my data has been read in by checking out my environment there, where I can see a little bit more information about this data set. And it suggests that I have 100 observations and 3 variables. You can even look at this data set if you would like to by selecting that little icon on the far right-hand side that kind of looks like a table. And so if you click it, it will pop up in that second panel there. And you can go ahead and see that I have an X variable. This is simply just a variable ID column there, followed by another column called group. This actually shows which technique was applied for each one of these students, along with their confidence score on implementing any type of R code. So one more time, your data needs to be set up in the following way if you're ever running an ANOVA where you have one column representing one factor or one variable with multiple levels. And the levels here are the different types of approaches or pedagogical approaches, methods that were used. That last variable there needs to be the scores across all of those methods. Okay. All right. Great. Now moving on. I really like to, in advance, explore my data a little bit more. I always do this. Exploration for me is super important. So I'm going to go ahead and note that I am exploring the data. And how I'm going to be exploring the data here is by using the function group by, which is actually within the dapplier package there. And so first I'm going to also list out the data set name, which is teacher R, and then I'm going to use that pipe function. Oh, excuse me, that pipe function. And that pipe function you can go ahead and implement by using your shortcut keys, Shift Command M. Make sure that you're careful if you're going to use that shortcut. Sometimes it can take you to a new screen, which literally just happened to me, but it's easy rather to navigate back. All right, and so now I can go ahead and note that I want to group our data using the group by function. And you can see that it automatically generates. And then you need to tell R which exactly variable that you are using or factor that you are using as a group variable. In this case, we are lucky that it is named group, right? And so then I'm going to be using another pipe here, right? Shift Command M, Shift Command M. And the reason why is because after I go ahead and group, I want to make sure that I end up getting summary statistics by group. Okay, so I'm going to use the summarize function. And I'm going to ask for summary statistics. Specifically, I want the mean, which is going to be a label for our mean of our score values. And so what I need to do is go ahead and give my summary statistics a label. It's going to be mean, and it needs to equal the mean function of our score variable. I'm not done yet. I need some more information, right? So I'm going to actually type in comma and then hit return. And then I'm going to type out SD because I want a column that represents the standard deviation of those scores for our groups. Okay, so SD score there, and then comma, and then I need my sample sizes. So N for the number of participants, so an N column, and that'll equal the N number of observations within that particular group. So one more time, on the left side here, I have what I want the label to be for this column. This column is actually going to contain mean scores of the variable that's named score. Likewise, SD is going to be the column name or the label of the column, and that's going to give me the standard deviation of those scores. And N, one more time, is going to be the label of that third column. And how I want that calculated is by giving me the N number of scores. And that stays empty because I want it for all. Okay. And so now I can go ahead and I can run this by either going anywhere in those lines of code and hitting command return, or you can even use that play button one more time. Right, so I'm doing that there. And one more time, you can see that mean and then SD and N are those labels for these columns. And then within those columns, you have your means for each one of those groups. And one more time, this represents the reported confidence level of our students who are applying our code after being exposed to a specific type of pedagogical approach. Great. All right, this is kind of giving me a sense of what is happening. And so I just kind of want to take this and I want to start running comparisons. And the way I can go ahead and do this is by running a one-way ANOVA. All right, a one-way ANOVA. And so I am just going to go ahead and implement and initiate another our code chunk. The first thing that I really need to do is I need to make sure that that group variable or that factor group needs to be known to be a factor within this data set that is in my environment. And how I can go ahead and do this is by using the as.factor function. And I'm going to type that out. So first, I'm going to leave myself a note. I am changing the group variable to a factor. All right, and so I'm going to type out as dot factor there, and you can see that it automatically generates. I'm going to go ahead and hit return for this function here, and then I'm going to, in those open parentheses, I'm going to type out teach underscore R, which is the data set and our global environment. Then I'm going to go ahead and type out $sign. When I do that, a drop down menu will fall. I'm going to then select group. If I wanted to, I could even type out group. Okay, and one more time, all I'm trying to do is make that group variable, that group factor, a factor in R. And so then I'm going to reassign this variable that I'm modifying back into that, that data set that I'm working with by typing out teach underscore R $sign and reassigning it to group. Okay. I can go ahead and run that. Great. Moving on, I can now go ahead and implement the AOV function, which is the function that we are going to use rather to evaluate differences among our group and the reported levels of student confidence using our code. So AOV, and then I can go ahead in parentheses, I can go ahead and type out what is my outcome first. In this case, it's going to be the scores. And then that is going to be predicted by the group. And this is actually coming from our data, which is labeled within our working environment as teach underscore R. And then I'm going to go ahead and assign this model here, option dash, to a name. Let's see if I can do this. ANOVA underscore model. Perfect. And I'm just going to leave myself a quick note here. I am running an ANOVA to evaluate differences among groups. Perfect. All right, and now I can go ahead and I should be able to run this line of code here. I think I have everything that I need. So let's go ahead, command and return. Great. So now I can go ahead and reference that ANOVA model because I have given it a name, and that object now, that model is now in my working environment, and I can see it in that first panel where it says ANOVA. And so now I want to pull the summary information for there. So now I'm going to pull that real quick. All right, so let's do this. So let's type out summary. And then when I do that, I can type within those parentheses there the name of our model. So it's ANOVA underscore model, and you can see that it automatically generates. I'm just going to go ahead and select it and then hit command and return, and all of that information will be given to me. And the first thing that I am seeing here is that the omnibus F test is significant, suggesting differences in student reported levels of confidence across those different teaching styles. Okay, and so I do want you to know, regardless of whether or however, the F test does not tell us where those differences are. We don't know if all of these approaches are actually contributing to those differences that could be occurring within the reported coding confidence. All right. And so this is when we now need to further investigate where those differences are occurring, either using ad hoc or planned contrast. In this case, since I've already stated that we kind of know what is the gold standard, I have in mind some set planned contrasts, and we're going to be going over those shortly. So let's go ahead and set those up. To do this, I need to first initiate another R code chunk here. I'm going to write myself a note, planning contrasts. All right. Now, the thing that I want to note here is that I'm going to be using the cbind function because I'm going to be making two technical contrasts here. I'm going to be comparing the gold standard of ASCL to all other methods, and also ADRI versus the flip and the pair pedagogical approaches. And so how I'm going to do this is by just listing them in the cbind. And so once I go ahead and type out cbind, these open parentheses will generate. I need to give my contrast some sort of label here. And so this is when I'm going to type out, for instance, I could type out something very descriptive or something very short. So I'm going to type out ASCL, V, and then I'm going to type A methods. So for doing my comparison here, and then I'm going to put that to equal. And then I am going to go ahead and then I'm going to concatenate a group of values here that relate to my contrast. And I just want to remind you all, they're kind of just all on and off buttons. And that's how I think about them, right? Where we need to have a balance here. And so that's why I have -3 as my first value, because that is my first group here, the ASCL. So I'm going to go ahead and type out -3 because I want to compare this one group to all other groups. So 1, 1, 1. One more time. I should have a balance of these values such that I could take them all and then they should equal up to 0. All right. And then one more time, I want to go ahead and also compare. I want to compare ADRI to all other to the other methods, flip and pair. So I'm going to add another contrast there. And so in this case, I'm going to type out ADRI, V, and then I'm going to type out flip and then pair. Just one more time. These are going to be labels that we are going to be seeing shortly when we are doing our contrast. And then after I go ahead and do that, I'm going to type out equals the following contrast, which we're going to concatenate these values of 0 because we don't actually want to compare the ASCL group there. What I want to do is I want to compare the flip, which is that second group, and then I want to go ahead and compare the third group, which is the pair group, I believe. And then I want to go ahead and compare those to the ADRI. And so I need that value to be 2 there. And then I'm going to go ahead and assign this, or you can even put an equal sign there, assign this to contrast. And then I'm going to, in those parentheses there, I'm going to go ahead and state which variable is my grouping variable, because this is where my contrasts are occurring. Okay. And so teach R, I type out teach R and that automatically generates. I'm going to go ahead and use the $sign, a drop down menu will fall. I need to go ahead and select group. All right. All right, I think this looks good. I just want to make sure everything is closed. Everything looks all right. Okay, I'm going to go ahead and I'm going to run that line of code. And it seems like everything ran well. All right, next I want to go ahead and just quickly look at those column sums. at those column sums. All right. And so let's go take a look at them. So column, moving at column sums. All right. And so I'm going to type out call and then big, or rather uppercase S, and then lowercase u, and then ms, and you can see that it automatically generates. I'm going to then type out contrast in that open parentheses there, contrast, and then teach group needs to then be typed out in that second pair of open parentheses along with that group. All right, and so then, go ahead and check this out real quick. You can see that I have our contrast here and that they should all equal to 0. The one thing that you do see right next to that is a third kind of contrast. This third contrast actually is equal to 0. I don't know if you can see this exponential. It is way out there. And so what this is technically R is suggesting that there's just a little bit of comparison left that has not been explained, but it is so tiny, and so we technically need to ignore it. Okay, we need to ignore that last comparison that could be coming up or that could be generated by R. Once again, it is so tiny, it is so small. And so another way that we can go ahead and view these contrasts is by typing out simply or printing out those contrasts. So I'm just going to copy and paste that assignment name there, contrasts, and then in the group parentheses. So let's print out print. All right, and then I'm going to go ahead, once I paste that assignment object name, I'm going to go ahead and hit Command Return, and then I can go ahead and then I can see that my contrasts have been appropriately applied to my two comparisons. One more time, there is that third one. Look how small those values are. They are to exponential of -16. They are so, so tiny. And one more time, this is our trying to implement a next set of comparisons or contrasts. But one more time, they are theoretically not important to this moment in time where I have suggested I'm only interested in these two contrasts. So one more time, if you're interested in only two contrasts, but there are a lot more than that can occur, or we'll try to find those other ones that are not yet explained or not yet set up. And so it is our responsibility to ignore this last column. Okay. Great. And so now we can go ahead and we can then start going into running the ANOVA with contrasts. And so this means that we are going to be able to do our comparisons and find out which comparison is significant and which is not. All right. So run on ANOVA with contrasts. All right, and so all we have to do is, again, implement the AOV function. And then within the AOV function, we want to go ahead and note what is going to be the outcome. And then that is going to be our students' confidence scores there. And they are going to be predicted by using that tilde, by group, and then comma, and then the data is coming from the teach R data, which we went ahead and we noted that our contrasts were that is part of that grouping variable. And we can assign this then to a new object that is going to be housed in our working environment there because we want to be able to reference it later. I need to go ahead and then use the assignment function to go ahead and give this model a name. In this case, I'm going to name it contrast. underscore model. All right, cool, great. So let's move on. Let's do this. I can see that it has run, or that rather it ran, and it is in my environment now. And I can go ahead and reference it for future summary evaluations. So I'm going to do that. So let's find out what this looks like. So report summary findings is my note to myself. And then I'm going to type out summary.lm. And then I want to note the model name. In this case, it's going to be contrast and then underscore model. Perfect. And it automatically generates. I can go ahead and then I can run that. Awesome. And the first thing that I can see here, oh, let me see if I can pop this out a little bit more. I guess that's not as useful as it is in the HTML file. So let me pull that up. What we can see here is that we can see that the comparison or the contrast between that gold standard and all other methods is actually approaching significance by that little dot there. And then you can see that probability of 0.056, so it's approaching significance. And one more time, if this is the case, we just move on and we don't actually evaluate this contrast. And what we could evaluate is then the group ADR versus the flip and the pair pedagogical approach, and we can see that these are significantly different. These two approaches are different from the ADR approach taken together, right? And so then one more time, this last final line here, that group line, is part of uh, that kind of that default that R is doing, and R in this case is trying to create a last final contrast. And one more time, it would not be theoretically just for us to interpret that final line there. So we would move on and we wouldn't acknowledge it whatsoever. All right. All right. And so next, I do want to show you that you technically, once you do this, you want to make sure that your contrasts are orthogonal, reminding you all that orthogonality has to do with independence. Independence. So making sure that the data that we are using for these contrasts are independent across all comparisons. And so we can do this by simply, we're going to create a matrix. So rather not simply, but we are going to create a matrix. So Option Command I to initiate that next R code chunk. And then I just want to look at this matrix. Matrix. I'm leaving myself a note here that I'm evaluating the matrix of our contrasts. And this is how we figure out if we have orthogonality. I'm going to show you just how. So I'm going to type out contrasts. And then from there, I'm going to go ahead and type out what is the data set name, teach underscore R, followed by that grouping variable, which is literally name group. A drop down menu will fall. I'm going to select it. I'm going to then assign this contrast to a label or to a label for the object that is going to be housed in R. In this case, I'm just going to call it contrast matrix. Okay. And I'm going to run that. And now I know that it's technically there because I can see it. It's in my environment. Awesome. All right, now to really know if our contrasts here are orthogonal, what we need to do is that we need to take the we need to take the transpose of our contrast matrix and we need to multiply it by the contrast itself. I do want you to know that I ended up adding a rounding argument around this other argument. And the reason why is because sometimes those decimals can just be a little bit off. And so it can be kind of tricky to go ahead and to determine if there are zeros on the off diagonals. So I'm just going to copy this real quick, just for time's sakes. All right. I'm writing myself a note that I'm evaluating the contrast matrix here. All right. And if you really just want to copy all that code, I do have for you that clipboard function where you can just simply select that clipboard icon and then it will copy all the code for you. So you don't actually have to write all this code out. And so I'm just doing it to, I don't know, encourage you all to do the same. All right, to do the same. And so the first thing that I need to make sure if is rather that there are zeros on my off diagonal of my matrix here, and there actually are. And I can see underneath 12 there are two zeros, and above 6 there's a 0, and below 6 there is another 0. Okay, so suggesting that we have met technically orthogonality. But since this is a video on pairwise comparisons and to deal with type 1 error and using different approaches, I am going to continue just as if we were doing this for non-orthogonal contrasts. All right, so the first thing that we need to do is that we need to first pull those pairwise comparison p-values. All right. So let's initiate an R code chunk together. I know what my p-values are when I navigate back up to those summary findings. Let me go back to those summary findings here. I can see my p-values here. So my first one for my first contrast is 0.056 and my second one is 0.023. I'm going to need those to kind of stack them and then use them for the next type 1 error controlling methods. All right, so let's do this. I'm going to write out a note to myself that I am concatenating or C-binding, rather concatenating p-values. And so let's go ahead and type out C for concatenate, open parenthesis, and then I'm going to type out those p-values that I have for my contrast, 0.056. Next one is 0.0123. I'm going to assign this to an object that's going to be housed in R, and I'm going to label it p-values or p-vals. Great. Moving on. Now I am actually going to apply the most common approach for dealing with type 1 error, and that is the Bonferroni method. One more time, synonymous with family-wise error rate. All right, so let's type out a note. This is me applying the Bonferroni. All right. And so then all I need to do, or rather what I need to do, is I need to use a function p dot adjust. And you can see it automatically generates. And within that argument or within that function, I need to note that I need to evaluate the following p-values that are housed within my environment there that I have just went ahead and assigned. And then I'm going to go ahead and hit comma, and then I need to specify the method. So I'm going to type out method. You can see it automatically generates. And in quotes, I'm going to put in Bonferroni. All right, and I can go ahead and actually print that out or type or run that. Great. And so then it's going to give me my adjusted p-values, what my p-values should be if I went ahead and I used a more stringent approach to reduce type 1 error. All right, and then let's do this also for the Hochberg. So let's initiate another R code chunk here, and we're going to use the same function, p dot. First, I'm going to leave myself a note. Hochberg adjustment. All right. So first, I'm going to type out p dot adjust, and then I can go ahead and select that argument or that function that pops up. I'm going to note that my p-values are in the following object that is named p-values. It automatically will generate. I'm going to go ahead and add a comma after that because I want to specify the method. So type out method, and that is going to equal the Hochberg. And then you have to specify the Hochberg in those quotes. I can go ahead and hit return after that, or command return. All right, and so every single time we're running a new approach, you can then see what those p-values are adjusted to, see if there are any significant differences or that we can evaluate the significant differences within our contrast. All right, and then after that, we can go ahead and then implement the Benjamin Hochberg. So let's do that real quick. So let's initiate the next R code chunk. Option Command I, just a quick reminder there. And so we are going to one more time write ourselves a note saying that we are implementing the BH approach or the BH method. And so to do that, you can use p.address. Great. And then within those open parentheses, go ahead and type out p and then val and then comma. And we need to specify the method by typing out method and then equal. And then in quotes rather, type out BH. BH. Perfect. And let's go ahead and we can get those adjusted p-values. I also have a way for you to look at all of them together. And so I'm just going to copy those lines of code and implement them, or rather paste them into an R code chunk starting on line 76. I'm going to run that so I can show you what this all looks like. Give me 1 second. Let me print this out for you all. And so then you can see for my contrast here, I have first the raw p-values followed by those adjusted p-values using the Bonferroni method, then the Šidák method, and then the Hochberg method, and then the BH method. All right. Great. So one more time, these rather are the different types of methods that we can use to control for type 1 error. And you can see that we're using them on our p-values here. I actually give you extended code for all contrasts in the HTML file, just in case if you were ever to do something like that in the future. I hope you all learned a little bit about the different methods that you can use to control for those type 1 errors when making those contrast comparisons. All right, see you soon.